Okay, so guys, today what we're going to do is we are actually going to, as I said, wrap up Chapter 8. Wrap up the fundamentals of covalent bonding, and we're going to do that by talking about something called resonance. Now, what you need to do is grab your books, and interestingly, in order to talk about this, you need to open your books to Chapter 9. And specifically, guys, open your books to page 356. So guys, here's the way this is going to go. We are going to talk about resonance. It's a concept. Well, it really happens. It's not a concept. But it's a phenomenon that you need to understand conceptually. The thing that's going to make resonance difficult is figuring out how to talk about it. Although you really won't talk about it unless you're speaking with other students. You'll write about it. But how do you write about this well? And so I'm going to give you a laundry list of things to say and things not to say when you write about this stuff. And then, guys, once you understand the concepts and how to talk about it, we're done. Then what I'm going to do is I'm going to quickly flip through a couple bullet points relative to some things that are foreshadowings for when we get back after the weekend, and then you're going to have time to work on your homework. You ready to go? Goes like this. Guys, consider, if you will, a molecule of ozone. Some of you may know, maybe you don't, that ozone is O3. You guys know about the problem we're having with ozone, right? Although it's fixed now. Did you know we fixed the ozone layer? I think it's all better now. Yeah. Isn't it? Oh, is it not all the way better? It's getting better. Guys, so ozone is an O3 molecule. You guys understand that oxygen is diatomic. Ozone is triatomic. It's literally 3 oxygen atoms bonded together in a chain. So ozone is a very important gas that hovers in our atmosphere. It acts sort of like a solar blanket, keeping radiation from getting in. They found out some time ago that we had a huge hole in our ozone layer above the North Pole. Actually above both poles. They figured out later that it was the result of chlorine ions being released into the atmosphere. We'll talk more about that chemistry when we talk about catalysts. But guys, here's the thing that's interesting about ozone. You cannot accurately describe ozone with one Lewis dot structure. And remember, we talked about carbon dioxide, right? And we said that you can describe, well, here, I don't want to draw it. You remember that we said that you can describe carbon dioxide as double bonds or a single and a triple bond, right? It's not what we're talking about. What we are talking about are Lewis dot structures where you finally get to the point where you're drawing them, that you can draw them in 2 different and yet equal ways. So let me show you what I'm talking about relative to ozone. So guys, the idea is this. Ozone is O3. And its Lewis dot structure, you may want to write this down. Its Lewis dot structure looks like this. Now guys, here's the thing that's interesting about ozone. When you draw its Lewis dot structure, you end up with a double bond and a single bond existing between the central oxygen and the outlying oxygens. Now, you may remember that double bonds are stronger than single bonds, right? You knew that? Okay, so double bonds are stronger than single bonds. So, and this is an important idea, which one would you expect to be shorter? The double bond or the single bond? The double bond. Why would the double bond be shorter? Stronger, more attraction, more tightly pulled together. And guys, that is true. Double bonds are shorter than single bonds. That is always true. Double bonds are always stronger and shorter than single bonds. But guess what? When you take an ozone molecule and you measure the bond lengths, Guys, this bond length is actually about 1.3 angstroms, 1.278 angstroms. So what should this bond length be? Shorter, right? Guess what? When you measure the length of that other bond, it's exactly the same. Now understand, this is not refuting the idea that double bonds are shorter than single bonds. That is true. So guys, what's going on? Well, the thing that's going on is this. If you measure the length, let me see if I can do this well. If you measure the length of an oxygen-oxygen single bond, and if you measure the length of an oxygen-oxygen double bond, here's the interesting thing that you find out. That an oxygen-oxygen single bond, how would I do this, is greater than? The bond length is greater than 1.278. And if you measure the length of an oxygen-oxygen double bond, it's actually shorter than 1.278. It turns out that this bond length sits between the length of a single bond and a double bond. So what is going on? And guys, the answer is this. This double bond does not exist right here. And that single bond does not exist right there. What is actually happening is that this double bond exists in both directions, partially simultaneously. I know. But guys, this is actually what happens in an ozone molecule. So let me offer this to you maybe as a way of thinking about this. Do this with me. You ready? Do this in your notes. So we are going to do the orbital, we are going to do the Lewis dot structure for ozone, right? Just like we did in homework. We're going to draw the Lewis dot structure. So we do this. There are 18, 3 times 6, 18 valence electrons for 3 oxygens. We've got 4 on the board, so that leaves us 14. So guys, when we spread out then these 14 electrons, let's spread them out as much as we can. So we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? Now, the oxygens that are outlying, the ones on the left and the right, they have full octets, yes? Now, what about the central oxygen? It doesn't have a full octet. So what do we have to do? Create a double bond. Where? Do we create a double bond here? Sure. Can we create a double bond there? Sure. So which one does it do? And the answer is both. Guys, what happens is this oxygen double bonds partially in both directions at the same time. And there's a name for this. This is what is called delocalized pi bonding. And you need to scratch that in your notes. This is what is called delocalized, oh, yep. There's number 1. Although I am finding I don't have to quit stuff. I can just do this and it comes back. Delocalized pi bonding. So guys, what does it mean that something is delocalized? It is without location. And guys, that's what we've got going on here. The double bond that forms, and you guys, have we talked about sigma and pi bonds? No, let's do this really quickly. So guys, when we have a full double bond, this is made up of one bond, which is called a sigma bond, and the other bond, which is called the pi bond. Then if we've got a triple bond, like exists between nitrogens, that's sigma and pi and pi. We'll talk more about this in chapter 9, but you need to know a little bit of this now. So a single bond is a sigma bond. A double bond is sigma and pi, and a triple bond is sigma and 2 pi's. So when we say delocalized pi bonding, what we're saying is that the second bond, This is sigma and this is sigma. But the second bond, which normally makes up the double bond, happens in both directions simultaneously. So what we end up with is half of a double bond this way and half of a double bond that way. And those half bonds are not as strong as a full double bond, but stronger than a single bond, and these are what we call delocalized pi bonds. Yeah. It does. What happens is that these guys share and these guys share, and you end up with half of a bond forming in both directions simultaneously. I'll show you better pictures of it in a minute. So guys, do you understand the fundamentals of this? Okay, so let's bring this together then, and let's talk about how we're going to represent this, because this is important. So, how do we do this? Well, guys, these are the two structures then that can exist for ozone, right? You want to write these down, because this is important, and you guys know that the AP gods drive me nuts, right? The level of detail that they expect. Guys, this is what they expect. If you saw a question on an AP test, and you probably will, not necessarily ozone, because a lot of molecules do this, but if you saw in an AP test and it said, draw the structure of ozone, okay? And they would tell you that ozone is O3. They wouldn't expect you to memorize that. If you drew that as the structure of ozone, it's wrong. That is not the structure of ozone. Ozone is not a double bond and a single bond. If you drew this as the structure of ozone, you'd also get it wrong, because it's not a double bond and a single bond on the other sides. So what is then the structure of ozone? It's the average of these two. See what I'm saying? So how do you represent that? And guys, the only correct way to represent that is with a double-headed arrow between the two structures. Now guys, let's talk about some terms. You ready? Oh, and by the way, let me vent a little bit. If you draw your double-headed arrow this way, they'll mark it wrong. Seriously. Because what does that double-headed arrow represent? Equilibrium. And they will actually mark it wrong. Your double-headed arrow has got to be, forgive my pen dragging, has got to be like this. If you draw an equilibrium arrow, they will not give you credit for it, because it's not reaching equilibrium. It is in fact an average, and equilibrium and average are not the same things. Yeah.
So if we draw that
You also get that wrong too. Yeah, neat, huh? Yeah. Okay, so guys, let's now talk about the words that we are going to talk about that describe this reality. You ready? So, what kind of bonding exists in ozone? Delocalized pi bonding. So we are going to talk about delocalized pi bonding. You cannot abbreviate it. I just did because we already wrote it down and I need more space. But guys, this is what is called delocalized pi bonding. When you have a molecule that exhibits delocalized pi bonding, that molecule is what is called, I pray my pen will let me do this, a resonance. All right, I'm just going to have to go across. I was hoping to not do this. Let me just clear this off. This isn't going to work. So, delocalized. This is what happens when you're running drivers that are not actually supposed to be working and you faked it. Okay, so guys, delocalized pi bonding, these molecules are then what are called resonance stabilized molecules. This is a and it's not molecules, it's molecule, it's singular. Guys, this is what is called, and I'm doing my best with my pen, it's really the best I can do. This is what is called a resonance stabilized molecule. And this bonding that comes as the result of delocalized pi bonding is what we call resonance. This is the phenomenon is called resonance. Now, when we talk about resonance, we give names to each one of these structures, and these are what are called conformations. Or you could also call them resonance structures. Those two terms can be used interchangeably. So guys, the big idea then is this. Ozone is a resonance stabilized molecule. It is a resonance stabilized molecule because it contains delocalized pi bonding. As a resonance stabilized molecule, it has two conformations or two resonance structures. And guys, those are the terms that you can use as you talk about what's going on within ozone. You get the idea? You okay? I'll let you write all this down if you still need a second. Y'all caught up? You good? Okay. So guys, with all of that said then, here are the no-nos. Do not do this. This will get you in trouble. When you talk about ozone, again, you know these terms, it is just fine to talk about these four words. Resonance stabilized molecules, conformations, resonance structures, and remember that these are equivalents to each other, and then delocalized pi bonding. Guys, do not use the term 1.5 bond. That is not what is going on here. This is not a 1.5 bond. It is a pi bond that exists in multiple directions at once. Also, do not talk about resonance bonding. There is no such thing as resonance bonding. It is delocalized pi bonding. And not resonance bonding. What's that? Those are the only two terms that are off limits. But guys, it's important that you understand this. Ozone is not flipping back and forth between those two structures. It is actually the average of those two structures. It's not flipping back and forth, which can be kind of hard to picture. So as soon as you're caught up with me here, I want to offer you another example and maybe some better images that'll help you better grasp what we're talking about. Can I give you another example? Y'all caught up? You guys are good? Okay, so let me offer to you this. I'm going to go white screen and hope that this doesn't break anything. Guys, do this. Draw the Lewis dot structure for nitrate. Do it in your notes. Maybe. Although it would be unfortunate to give you a molecule that doesn't have delocalized pi bonding as an example of another way to think about delocalized. Just saying. Okay, yes, it has delocalized pi bonding. Are you done? Not quite. So guys, as you're working on this, I'm going to take a swing at it as well and see how I do. So I know enough experientially that when 3 oxygens bond to a nitrogen, it actually takes on a trigonal planar structure. So I'm going to draw it like this. So this is 5, this is 18, and this is 1. So that gives me 24. I've already got 6 on the board. So that leaves me 18. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, like so. Good? Not good, but good to hear. Okay, so now the oxygens are all happy, right? Nitrogen, not so much. It needs 2 more electrons to fulfill its octet. What do? Create a double bond. Where do we do it? Pick an oxygen. That is classic delocalized pi bonding. Because guys, this double bond does not have to pick a location. This double bond actually forms in all 3 directions simultaneously. So what on earth does that look like? Grab your books, which are already open. 356. So guys, in the margin in blue and pink are 2 representations of what this could look like. So guys, if you look at the top picture, if you will, notice that they very clearly identify that as a localized pi bond. So guys, sort of get a feel for that. This is actually what a double bond looks like. If nitrogen and oxygen really did just double bond, this would be the sigma bond, and then the double bond would exist above and below the bond axis. And those 2 lobes together that they represent in pink are the pi bond. So guys, if the nitrogen and oxygen in NO3 just picked a place and created 1 double bond, that is what NO3 would look like, where those pink lobes between the nitrogen and the oxygen are the pi bond. But that is not what happens. What happens is this bottom picture. And what you end up with is that pink, they're not really pink, but that pink pi bond existing in all 3 directions simultaneously. And this is actually what delocalized pi bonding looks like, where that pi bond exists in all 3 directions at the same time. So, how do we represent that? Well, guys, the answer is not like this. So what we would do is we would take this and we would move these electrons in here and we'd have that. But that is not NO3. What do we have to do? We have to draw the other 2 conformations. So we very carefully draw the correct arrow, and then we draw this conformation and we put the electrons on, and then we very carefully draw our arrow. Which one am I missing now? Bottom left. And then we draw this conformation with the valence electrons, and that is how we represent nitrate. Yeah. Yeah, you actually do. I need a new board, like so. Yeah. What's that? Quit it. No. You're going to have to draw 3 brackets. So guys, what does that look like? Look, they did it for you in the book, right there in the blue box. See it? That is how we represent the resonance stabilized or the resonance structures for nitrate. Now guys, here's a little interesting ditty if you're playing along at home. This is why all nitrates are soluble in water. Remember when you learned about the solubility rules and you learned that all nitrates dissolve in water? Guys, the reason all nitrates dissolve in water is because nitrate looks like this. The idea is this. Say you've got sodium nitrate. When sodium and nitrate go into solution, they break apart, right? It's a strong electrolyte. So you've got sodium ion and you've got nitrate ion. But guys, the thing that would keep this from dissolving is if the nitrate wanted to come back and grab a hold of the sodium in order to regain stability. That's why things don't dissolve in water. Well, guys, it turns out that nitrate doesn't have, forgive the term, but doesn't have a desire. It doesn't have a need to get back with the sodium because the nitrate is stable all on its own because it creates these stabilizing structures through delocalized pi bonding. And also that, but nitrates are soluble no matter what they're bonded to. Yeah, go ahead. Because if there isn't one, good question. And the answer is that, let's say, how can I say this so it makes sense now? So why does it bond in the first place? Because when it takes the, it's a bigger answer. Ready? This doesn't resonate. That's not nitrate. Okay? Nitrate doesn't resonate. This is nitrogen trioxide. It's a molecule. It's a gas. It doesn't resonate. But what happens is when this molecule takes an electron from sodium, it becomes this and it resonates. But in addition to resonating, it also now has a charge. And that charge is attractive to the charge that's created when it takes the electron from the sodium. When that goes into water, the water molecules surround these ions, carry them off into solution, overcoming that attraction, and then allowing them to stabilize without the need for the other. So yeah, by the way, guys, be careful about that. If they throw this at you on the test and ask you to draw the Lewis dot structure, it does not resonate. Yeah, exactly. Good point. Yeah. Not acetone, acetate. All right, there's a very real chance I'm going to put this question on the test. So I try to avoid it, but you ask. But chances are good we'll talk about it right now, and half of you will get it wrong anyway. So let's just go ahead and talk about it. So here we go. So acetate is interesting, right? Because so this is acetic acid, vinegar. Now, here's the thing that's interesting about acetic acid. You take the hydrogen off of acetic acid, and it leaves its electrons behind. Oh gosh. And you get, that was me cussing on the inside. Okay, so how much damage have we done? Okay, that should be a circle. Good heavens, as if my writing couldn't get worse. And you end up with this. This is an acetate ion. So you kind of have the context of acetate. Well, guys, imagine that you were doing the Lewis dot structure for this from scratch. So acetate is this. So we go C, H, 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 C, O, O. So that's acetate. Now let's count electrons. We've got 4, 3, 4, 6, 6, and 1. So what is that? That's 7, 11, 12, 24? I can't add. Is that right? Is it 24? Okay. So we've got 24 valence electrons. We've got 2, 4, 6, 8, 10, 12 already on the screen. So that leaves us with 12. So we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Get it? What's acetate do? Well, we're not done, right? Who doesn't have a full octet? That second carbon. How do we give it a full octet? Create a double bond to oxygen. Which one? Both. Yeah? Guys, acetate is also a molecule that resonates. That's why acetates are always soluble as well. I think that's where you were headed with that. Yeah.
So we draw acetate.
Yep.
Then we have to draw our sample.
Yep. So technically acetate then would be this. Come on, baby. And that. And then the other structure, which I'm just going to chicken scratch and not care what my stupid board does, would be that. Hey, at least it let me get through it that time. And then again, you'd have to put them in brackets and so on and so forth. Yeah?
So whenever there's an option between double bond and
No, I know what you're saying. So let's say it this way. If you get to the point where in order to fulfill octets, you need to create a double bond. And that double bond could be created in more than one equivalent location. Okay? So for example, and this isn't really even possible, but if that was a nitrogen and we got in that spot, those aren't equivalent. And therefore it's not going to resonate. What would determine which way the double bond would form? It can actually be determined by formal charge. You could figure out the formal charge with the double bond here. You could figure out the formal charge with the double bond there and figure out which one is favored. But when we have two different options that are equivalent, in fact, it forms in both. So do you see what I'm saying? But again, if they're not equivalent, it doesn't resonate. And you can figure out which one it is by doing formal charges. Yeah? You know, it's interesting. I would let you do this, but it's funny. So junior year, sophomore year in college, this is going to become your life, a model building kit. And it's actually funny because when you start fiddling around with these things, you're like, oh, hey, why can't we just make ozone a circle? And you quickly find out that the amount of stress that it would cause to make that become a circle is just not favored. It's called steric interference. And basically the bottom line is these things don't want to do that. For the same reason that if you were to replace these with carbons, you would find out that this molecule, which you can just see ain't gonna happen. That would be what is called cyclopropane, and it doesn't happen. It just causes too much stress. But if you pop this open, and guys, we're gonna be playing with these soon. If you do this, and this is what is called cyclobutane, that does happen, but it's less stressful. So it really comes down to a question of steric interference and stress. So, you guys, what's that? We just did. No, we do so little organic chemistry in here that no, we really don't. We don't need to. So, all right, you guys okay? You're comfortable with resonance? Because if you are, we're done. You're all right? Okay. So guys, here then are the other things that we need to talk about. I'm not even going to give you notes because you guys are just going to stare at them. So let's do this. Got it? Let's call this A, B, and C. Which one's shorter? Which one's stronger? Done. There's a whole section in your book that talks about what are called bond enthalpies, which, as you would guess, is the amount of energy necessary to break a bond, in the same way that lattice energy is the amount of energy needed to break the lattice. The stronger the bond, the harder it is to break, therefore the stronger and shorter it is, and the strong short ones are the triple bonds. That is all of this in a nutshell. There you go. Okay. Now, guys, this, and please don't write this down. Here's what's coming next time. And guys, I do want to cover this just a little bit with you so that you understand. Chapter 9 is where this gets fascinating, because we are going to take what you already understand about covalent bonding, and we are going to push it in directions that you hadn't considered. We are going to talk about molecules that don't obey the octet rule. We are going to talk about molecules where the central atom has 6 valence electrons, even 4 valence electrons, rather than the 8 that we thought they should have. An example of that would be something like aluminum trichloride. Aluminum trichloride is a molecule. It's not a salt. And it actually looks like this, minus the unbonded electrons. It's trigonal planar in structure, and it doesn't obey the octet rule. It actually forms a trigonal planar structure, and it's happy like this, and it fills up, and the aluminum does not fulfill the octet rule. Guys, we're also then, and this is fun, we're also going to talk about molecules that have more than an octet. For example, we are going to talk about something like PCl5. It's called phosphorus pentachloride. Oh gosh. It's called phosphorus pentachloride, and it actually looks like this. And you end up with a 5th chlorine hanging off this thing, giving phosphorus 10 valence electrons, and it forms a structure which we call trigonal bipyramidal. And we're going to talk about that next time in class. You already know linear, trigonal planar, and tetrahedral. Well, guys, what we're going to do in the coming days is we're going to talk about molecules that have more than octets. The d electrons get involved as valence electrons, and you can actually have 5 and 6 sets of valence electrons around the central atom, forming these trigonal bipyramidal and octahedral structures. Now, guys, the one thing that you do need to understand, and this is important before we go on, guys, what is necessary in order for there to be more than an octet? And the answer is you've got to have a D sublevel. So, guys, which is the first D sublevel? The 3D, right? What that means is the first elements that can have more than an octet are phosphorus, sulfur, and chlorine. Silicon doesn't have enough valence electrons to do it. But guys, these dudes up here, carbon and nitrogen and oxygen, cannot have more than an octet because there is not a 2D sublevel. Okay, so the first element that can have more than an octet is phosphorus, because phosphorus, being in the 3rd energy level, technically has the potential for a 3D, and in fact it does, as you can see right there. So it's not until you get to phosphorus that these things can have more than an octet. There you go. So guys, we're done. You have some time left to invest in getting the homework done. We are going to do these 5 questions, and we're going to KWL Chapter 9. So you all certainly have stuff